Okay, this video is to show the implementation of the direct analysis method once again using Risa 3D, the latest version of it, but this time we're going to analyze a portal frame. Okay, so a simple one bay portal frame will be used for our analysis purpose. By the way, this particular portal frame can be found by going to MASTAN'S.com essentially. So this is learning module number 9 from the MASTAN website. So if you're familiar with MASTAN, then you know what I'm talking about. If not, just Google MASTAN 2, I believe it is, and you'll be able to go to their website, and from there you can navigate to find learning module number 9. All right. So starting the model, of course, we go to settings. Always do that. Take a look at the basics. And here I'm going to be using the LRFD method. So I'll just go ahead and select that option. Everything else will be essentially left as is. We will iterate on the Tausa B factor, even though it's not going to make a difference. You'll find out later. Alright, let's go to solutions. Let's take a look real quick at our P delta settings. We'll keep the default value right now at as far as convergent tolerance at 0.5%. We will modify this later if necessary. And actually, I want to do that to show the impact. I may want to do that to show the impact of modifying this convergent tolerance. In this instance, we'll leave it as it is right now. For a P-delta analysis, we will select the geometric nonlinear stiffness matrix modification option. And if you want to know the difference between the two, you can, of course, go to Risa and help, and you can find out more information about the difference of the two. You can also watch some of the other videos that I have on direct analysis method using Risa 3D. Alright, so say OK. That's all that we need to do right now. Close out of there. Let's go ahead and start putting in some information. You click on nodal coordinates. Automatically, when you click on the screen, you'll get 0, 0 defined as far as your first node. This particular portal frame will be 12 feet high and a 20-foot bay. So I'm going in a clockwise direction as far as defining my node in this instance. So my second node will be at the 12-foot location in the x-axis, maintaining 0. And then we'll put this one at 20 and 12. And this last one is fine at 20 and 0. Save the file. Now I'll define my member. Of course, you see me click on members from the home tab. And these are the default settings that are out of the box with Risa. Just expand those just so that we can see what's going on. Here, for my columns, I will be using W12 by 58, and we will be bending it about its weak axis. It would also be 50 KSI still using the A992 standard. over here and pick up my W12 by 58. Okay, I'll just go ahead and put it in there first, and then I'll rotate the axis. Just so you see what I have in 3D. Go ahead and pull up the name. Alright, let's see here, take off this. That's interesting that the name disappears when it's on 3D, but okay, whatever. That's Risa. Oh, there it is, it's just also gray. Alright, so I'll come over here and rotate these sections. You can see right now they're oriented, their strong axis, if you will, is oriented towards like the X direction. Rotate that by going to our rotation tab right here, hit 90 degrees, and now it's the other way. Take a look at it in 3D. There you go. The beam that will be tying these two columns together is going to be a W24 by 76. Also a A992 section. By 76. Let's go ahead and put some supports. We will actually be using pin supports for this example. So you can see that this moment's frame will be, pretty flexible as far as what we would normally do in the field, but we'll use this for our example. It's not a, I guess, unusual thing to do to have a pin moment frame just as well. It's not the ideal thing when they have a earthquake or you have really large lateral loads, but for educational purposes this is acceptable in my opinion. So there we have it. Save the file. Now that we know the orientation, I'll just go ahead and turn off our 3D view for a second. That's simple. We've just defined the model. For what we're doing, there is no other specific modifications that's needed to this structural model. Alright. So now let's define some loads. Sorry, you go to the Home tab, you go to Basic Load Cases. I will not be using self-weight in this analysis, just so that I'm consistent with what the numbers are from other runs that I have with this same portal frame. So for load, I'm just going to use one load case to combine my vertical and load together. I'm going to put it all in one load case. Alright, so we'll just call this loads. You can separate these loads when you put it in, but this is just a definition of the load case, alright? So nothing special here, just to define it. It'll make our run really easy. And I'm gonna put in some loads. You'll see from that learning module, they want us to start off with case 1, I believe, and case 1 has a ultimate vertical load of 130 kips and a lateral load of 13 kips. All right, 10% of the vertical in this instance. And it actually wants us to model some imperfections. So they want us to model the geometric out of plumbness imperfection directly in the analysis. Let's go ahead and put in the loads. Continue with that. So in the Y direction, you can see all my settings. It's in loads here. Y direction, basic load case is what it's going to be applied to. Put in minus 130. Show directly. Now, we'll also, let's see here, if we could actually get away with just using that one load case definition. I believe we can in Risa. So I'll go ahead and change this to the X direction and add an additional load of 13 kips. Click to apply. There we go. No problem. Alright, next we will define a load combination that will be used for the actual analysis. So we'll just call this, it could also be called loads, but I'm just going to call it ultimate. We will implement P delta only on the compression for my instance. Okay, it's not going to make a difference, but I always just consider P delta stiffnesses as far as in compression. And the reason why that is because when you use just yes as an option, that implements stiffness adjustments to both compression and tension members. Tension members, if there's an element that's in tension, all in tension, and P delta effects is taken into consideration, then it actually increases the stiffness of the structure. And so for my purposes, I just want to focus on decreasing the geometric stiffness of the structure. All right, so I would use compression. But when you choose this option, you know, you're implementing it for both compression and tension. And if you wanted to, I guess you were in a situation where you wanted to kind of see whether or not you could use some of that increase in tension, stiffness to help your model, you can use the yes option. But this option will also, you know, implement a decrease for anything that's also in compression. So this handles tension and compression increases in geometric stiffness. So we'll select compression, just because that's the way I always do things. I'm a little bit on the conservative side when it comes to structural analysis and design. Alright, we'll select this basic load case. I could use load category, but as you know from earlier, I didn't define a particular category. I used the load case directly. My factor is 1. The loads are already at ultimate. There's no need to make any modifications to the magnitude of the load. Save the file and run the analysis. Now take note, of course, oh yeah, instabilities. That's because I'm running this thing in 3D. So I have to make some modifications here. So if you get this instability, I guess message from Risa, that's because you have something that's basically not a stable structure for the type of analysis that you're running, or you might have a structure that's just not modeled correctly because of some releases, and basically you have to have a viable structural model. So this is telling me that basically the computer has, the software has automatically detected some instabilities, and it locks it, so it actually is making internal corrections. So this is what it's telling me, and then it's telling me basically, oh, I could still run the analysis, and then I'll show you the nodes that I locked in order to have run your not your analysis. And it's asking me, do I want to continue? Uh, in this case, I'm going to say no. All right, because I want to go ahead and not have any error messages pop up. All right, I'll fix that easily by just clicking on this 2D icon right here. So now I'm running it like it was a 2D model. Right. There we go. Oh, I get a warning that basically some members were defined as a member type beam, but they're vertical. So I should change it into a member type for column. This actually doesn't make a big difference. All right, but for consistency, again, we'll go ahead and make it a member type for column, just because we don't want any warnings popping up that we could correct ahead of time. Those are these two columns right here, so we'll change it to member type column. So okay. By the way, those type of messages, as far as that member type, is kind of germane to Risa. All right, there we are. Now let's take a look at the. I guess we'll start off with the bending moment. Excuse me. And we'll take a look at it in the Y direction. Unfortunately, Risa's text right now, I don't want to go through a whole, tutorial, make this too long, but basically the text is actually the same color as the bending moment diagram, which is annoying in this case. And so you're not seeing it clearly, but another way to see that information would be to go to the details of the analysis itself and click on it, and you can see the maximum bending moment value at the top of this column. Alright, so that maximum value, using just a one element node, one element to node type of structure, is coming up to be 132 kip feet. At the top, you can see the deflection value that is given us here, and of course this is ultimate, so keep that in perspective, of about 5 inches. Now I'll just take a look at also what is its stress ratio, so to speak. So actually I could collapse this to make things easier. So I'll collapse each one of these calculation sections just so that we could kind of get to the answer faster. Alright, and it shows that this element is failing, and is controlled by the bending and axial interaction. and so we have a overstress factor of about 19% here, or if you want 12%, I mean 20%, sorry. All right. So this maximum moment value, like I said, you'll see it right here. That's that 132. Let's look at that on the screen, which will kind of give us more indication, a better indication of what's going on with both of them. Excuse me. Turn this off. Go ahead and put some colors to this. Let's go ahead and put some numbers to those colors. And if you run this analysis, I think I have one previously ran like this with robot structural analysis. We'll save this. Just go ahead and pull that up real quick for comparison purposes. Alright, it takes a second because I have a slower processor. My apologies. But so that particular model would be the one on the left. You see my other models that I have here for robot, there's a lot of stuff going on the screen, so maybe I should clean it up a little bit. But the real quick part of it is that you can see I have the same W12 by 58 columns, W24 by 76 beam, same load, 130. Apply that each one of these nodes, and a lateral load. You don't see the lateral load in this case, but let's go ahead and put that on and show the combination. There you go. So you see the lateral load of 13 kips being applied. So these are three different models. Number 1 and number 2 are the same structural, well, it's the same elements, but the difference is, as far as it's the same section size, the difference is I have an additional node at the midpoint of this one. But you can see, we have pretty much the same stress value of 20%, 1.23 in this case. Okay. If we look at the bending moment value, it's probably a little bit higher. I actually have this thing shown in kip inches right now in robot, so let me go ahead and change that to kip feet. Okay. Show the direct analysis model. Now you see the 136 value, 136.25 in this case, and as I said before, I click on this one, 136.65. Oh, I kind of screwed up a little bit, so we can go back and correct that. And what I screwed, this is 130. So where I screwed up, and I'm glad I did, so to speak, is that I haven't modeled the imperfections. Cancel the out of plumb imperfections. So I need to do that. See? That's why I have various models, so I can always go back and double check things. That's my method. No one's perfect. You always have to go back and kind of double check things. Right? It's an early Sunday morning for me, and so maybe I'm not firing on all cylinders. But I'm smart enough to know that I can double check and make my corrections. All right, so I'm going to go ahead and move these nodes over. Let's see, I'm on the modified tab, and I will move it globally. Yes, I will clear my results from the previous operations, and now I want to move this. My units are, I want to move it by L over 500 in the X direction. My units are in feet over here right now, and I will just go ahead and switch. Let me switch off units over here. Let me go to inches for a second as far as what I need to do. Alright, go ahead and select move. Now I'm in inches. Go in the next direction. L over 500 multiplied by 12 feet times 12, of course, will give me 144 divided by 500. So that'll be 0.288 inches. Alright, we'll apply it to our selected load, and it moved over a little bit. We can always double check that by hovering over that node, and we see its nodal coordinates, and the model is out of line. Make sure you take a look at your loads, make sure they're still applied at the same location, nothing funny is going on. Alright, now we're good to go. Run this thing again. There we go. Let's go ahead and take a look at what our moment value is now. It's not going to make a big difference, but you will see that we get a value that's closer to what I've shown in my other program. So 135.6 is the maximum moment here. Go ahead, pull it up. 136.25. So that's pretty close for what we're doing. We'll accept that. There are always going to be some type of slight differences in the numbers sometimes, but if I spend enough time, I can make it converge. Alright, let's go ahead and take a look at our stress ratios here. You'll see it probably jumps up to closer to that 23% overstress value. There you go, right on the head. Alright, save. Let's go ahead and show what does work. Actually, nope, let's do what we always do and increase our number of nodes here, our number of elements. When I say we always do is, this is for education purposes, so I would, I'm demonstrating what I would normally do as far as showing differences in the analysis, but what I would do as far as actual work for design is I would use a minimum of elements that have one node in the middle whenever I'm dealing with structural steel, concrete, or any one of these things, and that's because basically you get a more accurate analysis. So you must break your member into additional sections. This is something that is missed oftentimes by certain engineers. It gives you a more detailed analysis. So you must break it down into additional nodal sections to get more correct answers, if you will, or get the correct answer. All right, so let's go ahead and copy this thing over. And I'm still in inches. That's okay, because I can copy it over by 40 times 12, 480 inches in the X direction. Apply to the selected elements. There we have it. So copied, show. Okay. Again, you have to do things right, so make sure it was selected when you're copying things over. You select copy the loads and anything else that might be applicable here. So copy loads is the only thing that I need to do. Select that. There we go. Take a look at our sections. Make sure everything is cooking curry. Still the same stuff. But now, let's take this, take these elements, and we'll add an additional load to it. Sorry, go ahead and apply it to our selected. Save. And let's just go ahead and run the analysis. We'll see what happens. Do the other one that actually works. Pull up our stress ratios here. Still 123. Didn't really make a big difference, and that's because of the sensitivity of these particular elements to the loads that are applied. You don't see a big numerical difference here. We could click on this and you might see a jump in the moment value, but it just didn't make that much more of a difference. Alright, so not too much of a jump in the moment value, but we have an increase in the deflection value here. That increase is probably the same as what it was before, and that's basically because this stuff was wasn't modeled correctly. But let's investigate. So 5 inches for that model. No, still 5 inches on this model right here. So not that big of a difference. That's good. Using the shear, using the P delta method, the geometric stiffness method. Let's come down here, take a quick look at what we have, and you can see also, yeah, it didn't make a difference. Again, this is because of the sensitivity of this particular structure towards lateral deflection. It was basically so weak the first time, even one element did the trick as far as capturing the value. Alright, so that, that's a structure that's basically really weak. That's what it implies. Alright, when you don't have a big difference between these two type of elements. Okay, so that is what doesn't work. Let's see here. Turn back up here. Still 123. See, everything's the same. Now, go moving on. Case 2, if you will, for learning module number 9. Access to determine what does work. Alright, so what does work is actually a lower load. It's 110 kips in the vertical direction, and a lateral load, 10% of that, giving us 11 kips. And these are the results from robot. Alright, so I'll go ahead and do that real quick. Let's see if this stuff gets stuck. It's annoying, but whatever. So I'll go ahead and do that over here. You see, robot crashed. Alright, not a problem for me. I'm not going to send a report. Just close this out. That's fine. Come over here. Let's go ahead and the thing is stuck on no, so there we go. Copy this thing over once more. Excuse me. Take a look at everything. I'll change these loads over here. It's kind of nice that you can actually click on the node. And if you double click on the node, you might be able to change it directly. Alright. Or you can just select it all. Let's see. Hit delete. That will happen, so don't do that. Let's just go ahead and do it our traditional way. Let's see here. Actually, I can take it off from the load cases. Let me see what's the number here. I know what number it is. Number 13, number 12. I'll just modify it from the database. Make life easier. So at number 12, I'll put this at 110. Put this at 11. There you go. Save it. Run it. Pull up robot in the background in the meantime. There we go. What works? Voila. Let's go ahead and turn off our node numbers for a second. And you can see these elements are working at 95 and 94% overstress values. Okay. Let's save that. Love this annoying software sometimes. Pull up our last model. Doesn't even remember the fact that I had the other model pulled up. There we go. 95, 94%, 96%. Everything is the same. Alright. That's a wrap. So this is how you would do it for a portal frame. Sorry for the long video. I hope you enjoyed it. Peace.